Good morning, everyone. All right, so we will talk about Bitcoin today. I'm just waiting a few minutes for everyone to join, and we get started. We have a short presentation on the theory, how ICP and Bitcoin are integrated together, and then we will code something. We will try to code a canister that can own and send Bitcoins. So kind of like a wallet, on-chain wallet. We'll try to do that. Okay, I think we are on time. So let's get started. So yeah, we're talking about Bitcoin and ICP. So Bitcoin and ICP are two different networks, of course. And generally, the problem of moving assets from one network to another. So in this case, and I hope I can play the animation. Yeah, okay. So in this case, on this presentation, you can see on the left, the Ethereum network, on the right, the Bitcoin network. And traditionally, it has been a pain to move funds from one network to another. So for example, if you have Bitcoin on the Bitcoin network, they exist and they have a meaning on the Bitcoin network, but they don't exist and they don't have a meaning on other network. So the problem that we run into regarding blockchain is this problem of how do I use my funds on other network. So for example, let's say I am, let's call him Victor or Tom. Tom on the picture here, he has some Bitcoin and he wants to use that with Ethereum applications. So for example, he wants to use his Bitcoin on Curve or Uniswap, which are DeFi application on Ethereum. The problem is that his Bitcoin live on the Bitcoin network and they don't have any existence on the Ethereum network. But the smart contracts that he wants to use are on Ethereum. So how do we fix this problem? We've came up with a concept of bridge. Essentially, the bridge, which you can see in the middle of the picture, is an entity that emits something called wrap Bitcoin on the Ethereum network and controls a Bitcoin wallet. So essentially, you send the Bitcoin to the wallet. The entity is going to verify that you've sent a correct amount, and then it's going to mint on the Ethereum network the equivalent in wrap Bitcoin. And actually, we can take a look at the wrap Bitcoin because it's one of the most popular currency. I think it's probably in the top 20 or 30. Let me see. So I have CoinMarketCap open here. So wrap Bitcoin, oh no, actually it's not as much as I thought. It's 200, top 200, but still pretty popular currency with a market cap of 7, is it 7 billion? I guess, yeah, 7 billion. So essentially it's a copy of Bitcoin that exists on Ethereum, and it's supposed to always replicate one-to-one the value of a Bitcoin. Now, the problem with bridges, and we've seen a lot of hacks and problems in the past, is that those entities, those bridges are held together, or they are controlled by entities. Usually, you have several entities together that controls the wallet. So the wallet that is on the right, it's controlled by several parties, and they essentially they are trusted parties, usually like exchanges or big huge projects which have a lot of stake, so they don't necessarily have incentives to steal the funds. But it can happen, and sometimes on some chains or some smaller bridges, you have hacks or you have a team that decides to steal the funds. And so this concept of bridges has been, well, it has been painful for users, it has been painful for developers, it has been painful for almost everyone that got hacked. And it's just kind of a trick, but it's not a proper way to handle funds between network, or at least it's not the best way. So what we're going to talk today is a different approach to bridges. It's a native integration between two networks, which is very advanced and very cool. It can be summed up like this. On the Internet computer, canisters can receive, hold, and send Bitcoins. And they can do that from the Bitcoin network. So it's not a wrap Bitcoin, it's a real Bitcoin that they can own, which means that any canister on the IC has an address on the Bitcoin network and can sign transactions, and they can broadcast those transactions to the Bitcoin network. So it's really like two networks integrated together, and it's not a bridge, or it's not a wrap version. How does it work? There are two components to it. The first one is connecting the networks together. So essentially making sure that replicas of the Internet computer, so nodes on the Internet computer that you see on the left here, are connected to Bitcoin nodes on the right, which means that you can essentially track transactions or emit transactions. So you have a relation between the two networks. The two networks are connected. And essentially, each ICP node is connected to around 5 Bitcoin nodes to make sure that it's decentralized and I would say diversified. Those nodes are randomly selected. And regularly, there is something called the Bitcoin canister on the ICP network, which essentially is a copy of the Bitcoin network, but on the ICP network. So this is the canister that you can see on the bottom of the picture with the WebAssembly module and the Bitcoin on the top. This one is called Bitcoin canister. We could maybe take a look later at this canister and his interface. But essentially, this canister is responsible for storing UTXOs and tracking balances. So if you're not familiar with Bitcoin, essentially, you can think of it as a copy of the Bitcoin blockchain in a canister. Why do we do that? We do that so that any canister on the IC network, through inter-canister call, you remember we can do those inter-canister call, is able to call the Bitcoin canister and receive informations about the Bitcoin network. So essentially receive information about transactions that are completed or not, receive transactions about the balance, and so on. You can see that from the point of view of the canister on the bottom of the picture, the top bottom right, it's very easy to access information from the Bitcoin network. It's just intercanister call. So constant, I don't know if you can read, but it's essentially written const balance equal await management canister dot Bitcoin get balance. So essentially just a call, intercanister call, and you receive the answer. And it should not be const because const doesn't exist in Motoko. So there is a little mistake here. So that's the first part of the integration. There are two parts. The first one is the one that you see right now, which means connecting the two networks together and essentially copying information from Bitcoin on the ICP network. Now, the second part is more complex and required more engineering. So this was engineering done in the past 2-3 years by Definity. And the problem they try to solve is if you want to sign transactions on the ICP network, on the Bitcoin network, you need to have ECDSA keys. So ECDSA keys are the underlying cryptographic keys that are used by Bitcoin. Essentially, you have a public key, you have a private key. The private key can sign the transactions. The public key can be used to verify transactions. And this has been a problem. How do we store the private key safely? Of course, we cannot store the private key in one replica. If we do that, then the system wouldn't be secure. If we give the private key to, let's say, replica number 5, we are not safe because the replica could be malicious and could steal the key. Of course, we cannot store the key in plain text in the canister because otherwise people would be able to read the key and would be able to steal the funds. So we have to kind of create I would say, a trick to store this key on the ICP network, but still without anyone being able to steal the funds and steal the key. And so the trick is called threshold ECDSA. Essentially, it's using a new version of the ECDSA protocol that is shared across nodes on the ICP network. So essentially, the key is never stored in one place. It's stored in multiple places. And only through consensus, so only if 2/3 of the nodes, more than 2/3 of the nodes, are consenting to sign a transaction, you are actually able to create a signature. So essentially, you have your key, which is the one you can see on the bottom. And the key is divided in multiple shares. So here you have 6 shares, but it's going to be way more than 6. It's going to be, I think, around 30 different shares, and those shares are going to be distributed across nodes. Each node has 1 share, and only through consensus you are able to create a signature. Even the private key is never constricted, so there is not a single place and a single time in the history of the network where you have the private key stored somewhere. You only have those shares, and essentially it's the same as the ICP consensus. You have to have the majority of the nodes able to sign, and then you can create your transaction. You can create the signature, and you can broadcast the signature to the Bitcoin network. Also, shares are regularly shuffled around. So essentially, it's a very, how to explain, a very cool, very improved version of ECDSA, because even with the same public key, so the same Bitcoin address, you can have a different share of a different set of shares. So what do I mean? Imagine that one node leak is key, another node leak is key, and so on. The more time passes, the less secure the system becomes, because you can have more shares that are around in the nature, and they are at the mercy of an attacker. But actually, regularly, so I don't know exactly how much time, but I think it's maybe every day or something like this, the shares are shuffled and reconstructed. So essentially, you keep the same master key, but you shuffle the share and you create new shares. And so essentially, old shares become useless. And even if you find them, or if they are leaked, you wouldn't be able to steal the private key. So it's very low-level cryptography, and it required quite a few engineers and cryptographers, but this is what is used on the IC. And now that you have the two sides, so you have the networks that are connected together and you have this threshold ECDSA protocol, essentially any canister on the IC through inter-canister call with the management canister. I will explain what is the management canister exactly. You are able to create transactions and broadcast those transactions on the Bitcoin network. You are able to create accounts, so create Bitcoin addresses, because you are able to create ECDSA keys. You can check your balance, and you can also, of course, send transactions. And yeah, that's essentially a summary of what's happening. So you have random Bitcoin nodes. The ICP network loads blocks, so it's actually syncing the Bitcoin blockchain every round, keeping in sync with the Bitcoin network. The Bitcoin network is kind of copied or synced in this Bitcoin canister. The Bitcoin canister is controlled by nobody, and it's simply a copy of the Bitcoin blockchain that we need to have the access to balances and transactions. So this is the first part of the integration, and I can actually show you on the ICP dashboard. We have this tab called Bitcoin. So it explains, essentially this little paragraph explains everything I just said. And now you will see this thing called chain key Bitcoin. You will see it quite a lot around. And chain key Bitcoin is essentially the native version of Bitcoin on the IC. It's fully transparent and backed 1-to-1 by real Bitcoins. It's around 2-second transactions, and it's integrable with any ICP application because it follows the ICRC1 standard. And now the first thing that you might be wondering and asking yourself is, why do we have this chain key Bitcoin? Actually, that was my first question as well when I heard about this integration, because I thought the whole point of the integration between Bitcoin and ICP was that we use real Bitcoin and not wrap Bitcoin. So why do we still have this chain key Bitcoin? So we can use real Bitcoins on the ICP network, and actually some projects are doing it. But even with the Bitcoin integration with ICP, we cannot solve the problems of the Bitcoin network. So even when the transaction is broadcasted by a canister, you still have to go through the Bitcoin consensus. So you still have to go through high fees, and you still have to wait maybe 20 or 10, 20 minutes or 30 minutes for your transaction to be confirmed. So it's possible, we can do it, and actually most of the projects are doing it. But for, I would say, daily usage, like if you want to send something on OpenChat or you want to do like a quick transaction to pay something, this is why we have Chain-key Bitcoin. And Chain-key Bitcoin is a wrap version of Bitcoin, but the difference with the bridge that we've seen in the first slide is that the entity and the bridge itself is a canister, and the canister is controlled by nobody, and the code is open source. So you have high guarantees that essentially there is always a one-to-one relation between Bitcoin and Chain-key Bitcoin. How does it work? Well, there are two canisters involved. There is the minter and the ledger. The minter is a canister that you send real Bitcoin to. It's going to check, well, it has an address on the Bitcoin network, of course, a wallet. It's going to check after some transactions that you have actually sent the Bitcoin. Then it's going to send a canister call to the ledger. The ledger is the canister that stores the ledger for Chain-key Bitcoin and is able to mint Chain-key Bitcoin. So once the confirmation has gone through, you will receive your Chain-key Bitcoin. And then your Chain-key Bitcoin, you are able to use it in any ICP application. So I have taken the example of OpenChat. I can show you actually. On OpenChat, you have this possibility of, so for example, let me show you. So here in the crypto, yeah, here you are able to, so those are called Chain-key Bitcoin. and you are able to send them to any. So I could send that to any user of the Motoko Bootcamp group. You can select an amount, and it's essentially a 2 to 3 seconds transactions. So it's very fast, and it can be used in any ICP application. Let me go back. Yeah. So on the ICP dashboard, you can take a look at the Chainky Bitcoin transactions. You can see that people are using it. So 3 minutes ago, 3 minutes ago, and so on. And so the advantage, of course, is that the speed is, I mean, it's 2-3 seconds transaction, 3-second maximum. And also the fees are ridiculously low. So the fee for a Chainky Bitcoin transaction is 0.0000001, which probably is like a few cents, I guess. Let's do the so if we assume that one Bitcoin is around $45,000, I think that's the current price, and this is 0.001. So let's see. It's going to be not even 1 cent for a transaction. So as you can see, this is really, really cheap. Of course, there is going to be an initial fee when you convert to Chainky Bitcoin, because when you convert to Chainky Bitcoin, you can you have how to say it? Like you have to send your Bitcoin first. Like in this first slide, this first step, you have to send your real Bitcoin to the Chainky Bitcoin minter. And so this transaction happens on the Bitcoin network. And so there are fees associated with that that you cannot avoid, and there is no way to avoid that. But there are other ways to, get your hands on Chainky Bitcoin. So for example, if you go to a trading platform or a trading application on ICP, you can trade ICP for Chainky Bitcoin. So you could receive Chainky Bitcoin without having to convert your Bitcoin. Yeah, if someone else did it for you, you would be able to add this in this part of the slide. So on the ICP network, you would be able to get Chainky Bitcoin for essentially no fees. And so we can see at any point in time, this is the total supply of Chainky Bitcoin. So it's how much essentially Bitcoin are stored securely on ICP. So we are at 180 at the moment. So I would like to make, maybe I can make like a quick. So how much is 3? Okay, so it's 8 million. So $8 million of Bitcoin are stored on ICP at the moment. So it's pretty cool. And I won't talk about it in the bootcamp, but I'll probably make like videos later, some more advanced content. But there is essentially the same for Chainky Ethereum. So the same thing that we did for Bitcoin is also possible for Ethereum, because the underlying cryptography is the same. And the Chainky Ethereum has also, you also have this Chainky Ethereum, so it's essentially the same. You can mint and transfer and so on. So what are the use cases for that? The use cases for that are multiples, and I haven't listed everything here. So yep, okay, so the first one is this concept of social fi. So you are able to use Bitcoin in any social application, social network. And it's finally possible to use Bitcoin for like day-to-day transactions, because you don't have to pay those high fees. There is on-chain decentralized exchange. So this one is really big, essentially being able to directly transact on-chain and having a decentralized exchange that is where you are able to trade Bitcoin and Ethereum and ICP from multiple chains. So right now we already have this concept of decentralized exchange, but it's limited to one chain. So you have to go to those bridges to go between multiple chains. In the future, you won't have to use those bridges. You can just trade between different chains, different assets, and you won't even notice that you are doing that. Chain-key Bitcoin, of course, is a big use case. Crowdfunding, so any project on ICP could raise funds with Bitcoin or Ethereum. Actually, it's already possible. So it's a small, it's a small addition, but I think it's worth that. Essentially, if you raise funds, you can get people where they at, where they're, what they own. So I think it's great. Some people sometimes, some projects sometimes they force you to buy this currency and invest in them in this currency. I think the more options you have, the better your project will do, Ordinals marketplace, so Bionic recently launched. They have a marketplace for ordinals. So ordinals are Bitcoin NFTs. And essentially they have very, very low fees and 2 seconds transaction because they are using ICP as a layer 2 for Bitcoin. And non-custodial lending protocol. So essentially a lending protocol. So right now, most people that own Bitcoin, they do absolutely nothing with them. They just, they just store them somewhere. And a lending protocol would enable you to own an interest on your Bitcoin. The problem with that is that you have to give away the control of your Bitcoin, and most people would not like that. So the solution would be a non-custodial lending protocol. One of them is called Finterest. And they are able to do that because they are using GIC. And so they are able to make a canister own the Bitcoins and not Finterest themselves. So even if Finterest wanted to, steal your Bitcoin, they wouldn't be able to do that because they are using canisters and they are going to remove the control of those canisters. So of course you need to check how it works and you need to make your research, but this is something that is only possible to do on ICP, and that's pretty cool, I think. Okay, so let's code. Our goal is simple. We are going to create a canister that is able to own and send Bitcoins. Okay, and for that, let me just 1 minute. So we need to go to this GitHub repository. So I'm using the example repository from Definity. It's a great repository. You have many, many examples of how to build applications on ICP. There is a Motoko folder which contains all the Motoko examples. And the one I want to take a look at is where is this one? Yeah, basic Bitcoin. This tutorial will walk you through how to deploy a simple canister smart contract that can send and receive Bitcoin on the internet computer. That's exactly what I want to do. So let's follow the instructions. Okay. So we are cloning the repository. It's probably gonna take 1 or 2 minutes. Okay, so we can open this code base and see what's inside. So we have a defx.json, we have a canister, basic Bitcoin, and we have source basic Bitcoin main.mo. So this one, we have quite a few code to go through and understand. And we have Motoko Bitcoin. So this one is probably more, it's using like, okay. So I don't think we will take a look at this one for right now. We just use this one. So let's open the README on the right. So we have the IC SDK installed. They mean the FX. So The first thing we want to do is actually deploy this canister. So we are going to deploy it on the IC. I'm making sure that I am using my correct identity. Okay, sounds good. So DFX deploy network IC. And when we deploy this canister, we will notice that we have to pass a parameter. So this is the first time that we see that you can actually pass arguments when you deploy something. And the way to do that is to have an argument here in the when you define your actor. So we have this actor keyword as always, and now we have class, then the name of the class, and we have this argument network. And that's what we are going to pass to the FX, this one, with the argument flag. And you could pass more arguments. So for example, you could pass, could be used for all sorts of, environment variable, or if you want to have, this one is a good example because this canister could be used on the Bitcoin network. So on the mainnet, so on the real Bitcoin network, on the testnet, and on the, I don't know which one is which, I don't know what is the reg test, but what we are going to do today is use the testnet because I don't want to use real Bitcoins, of course. I want to use the testnets because I don't want to pay for the fees and everything. So let's deploy it. And so the argument that I specify here is passed here at the deployment of the canister. Let me know if I need to zoom a little bit. I think it's, yeah, like this would be good. Okay, so we have an issue. So unable to serialize candidate values, invalid data, unable to serialize candidate values, variant field testnet not found. Yeah, I think it's because it should be testnets. So there is a mistake here. I guess it should be testnet like this. I'll make a pull request. Okay, so we have deployed our canister, and now we can take a look at the interface. So this is the candid UI, and maybe first let's look at the public method that we have. So get balance, return the balance of the given Bitcoin address. Oh, sorry. Get UTXOs, get current fee, get P2P KH address, return the P2P KH address of this canister, and send a given amount of Bitcoin from this canister to the given address. So what is the P2P KH address? It's a specific type of Bitcoin address that we are going to use today. It is explained in the README of this repository. Essentially, if I open this file, it is the step 2. So step 2, generating a Bitcoin address. Bitcoin has 2 types of address. The first one is P2P KH and P2P CH. And those addresses can be generated from ECDSA public key. So essentially, we are going to generate a P2P KH address. And actually, I am not sure what is the difference between a P2P KH address and a P2P SH address. So if there are Bitcoin experts in the chat, maybe someone know, but I don't know what is the difference. And to generate our address, we are simply going to call this method, get P2P KH address. So I'm going to make a call here. It should take a few seconds. And we have our address. So it took 8 seconds. And now let's take a look at what's happening behind the scenes, because I want you to understand exactly what's happening. So this, it's here. So awaits Bitcoin wallet dot get P2P key address. We specify the network, the key name, and the derivation path. So this network is stored here, the derivation path is stored here, and the key name is specified here. Now Bitcoin wallet is here. So this is a module that we are probably going to put here. It's, yeah. So it's a module that we import here, Bitcoin wallet. And we are calling the get P2P key address, which is here. And this method is here. So it's the first one that is here. Essentially, it's calling ECDSA API. So you remember this threshold ECDSA that I was talking about? There is an API. If we look at ECDSA API, it's also a module. So we need to look into this one. And you don't have to understand every single line, but just the general concept. So ECDSA API.ECDSA public key is here. And so we are again calling another await method, which is the ECDSA canister actor. And the ECDSA canister actor is this canister, actor A, and so on. And this one, so this one, it's finally the management canister. I don't know if I remember, but 20 minutes ago, I've mentioned that I would explain what is the management canister. So now it's time to talk about it. So where can I find the best? Where can I find the best documentation for this one? The management canister is so it's looking like a canister. It's essentially an interface for a canister. Management canister. No, it's not. There is not like a good article or tutorial about it. It's like a hidden part of the network. Okay, so I don't see a good explanation of it. So I'll do it myself. The management canister is essentially an interface from the ICP network, which looks like a canister. So you can call it like any canister. You can do intercanister call with it, but it's not really a canister. It's essentially giving you access to network functionalities. So let me maybe give you an example. Actually, I am using it in the code of the Motoko Bootcamp dashboard. So if I show you how it looks like, it's this file. I have the management canister defined. Public type management canister is an actor, so it's a canister, it's defined as a canister, and you can call several methods on it. For example, this is how you could create multiple canisters. So if you want to create a canister from your canister, you would need to call the management canister. You can install code inside other canisters, you can deposit cycles, you can call the canister status, and you have way more methods that are not listed here. One of them is the ECDSA method. So you are able to generate ECDSA keys. You are able to call HTTP outcode. So every kind of system functionality, you can access the system functionality through the management canister by simply calling it. And once again, the management canister is not really a canister. It's just an interface that is made easy for you to be able to call it. So Okay, I have found the document where it's explained exactly, but this is a very low level and complex document. It's the ICP specification. So you can read it. It's very, very long and it's very, very low level. So good luck with it. And there is management canister. Okay. So the IC management canister is just a facade. It does not actually exist as a canister. And the address is the empty blob. So 5A and 2A. And essentially, that's all the methods you can call on the management canister are here. So you can create canister, update settings, upload chunk, install code, start a canister, stop a canister, canister info, HTTP request, ECDSA public key. So this is the one that we are calling, the ECDSA public key. Bitcoin get balance, Bitcoin gets balance, Bitcoin send transactions, and so on. So all the functionalities from the system, from the ICP itself, are exposed through the management canister. So we can go back to our example. What we are doing here is calling ECDSA public key, which is this method, and it returns the public key based on the canister that we have, the derivation path, and the key ID that we have selected. Okay. Now, oops, let's open that. So we have our address. Now the ID is going to be receiving Bitcoin to our address, and we need to use a Bitcoin faucet for that. So I am not 100% sure it's going to work, but let's try it out. And I need to specify my, so let's quit that. So this is my address, the address of my canister. I specified here, and I can get up to 0.00008 Bitcoin. Let's try with maybe, yeah, like this amount. So this is not a valid testnet address for some reason. I'm not sure exactly why. So something went wrong with how we've done it. Maybe no, I haven't. Well, this is essentially the same. Okay, so I can use maybe this. Let's see if this one. Okay, so this one seems to have worked. Maybe there are two test nets. I didn't choose the correct one. So probably we have to wait for this transaction. What is happening? Okay. Maybe I can check my balance. So I'm pretty sure it's gonna be 0 right now. Ah. So I just want to access the transaction. Uh, Okay. So I did not log the transaction hash, so I don't know how I can check. Maybe. Okay, so let's see. I have this testnet explorer. So this is my address, and there is no transaction recorded. So yeah, I don't know if I'm going to receive. I don't know if I'm going to receive the bitcoins or not. Maybe I should try again, but I don't want to abuse those testnet, because those testnet are also, like, even if that's not really valuable, they still have limitation on how much Bitcoin you can get. Okay, this is my address, and okay, let's try again. Oh, okay. Sometimes it takes a few days. Bitcoins are sent manually. Okay, so I don't think we'll get our token today. Okay, let me see. I should still be probably at 0. Yeah, okay. Well, let's assume that we have our Bitcoin received. And then, well, we would not be able to do step 4 and step 5. So I'm kind of stuck right now. So I think I thought the testnets were faster than that. It's the first time I try a testnet, so. Yeah, sorry guys. I think we'll stay here for today. I don't understand why the first testnet we use told me that my address is not a valid testnet address. Yeah. Okay, but in theory, if you give it a bit more time, you should be able to receive your Bitcoins. And once you receive your Bitcoins in the canister, well, you can check your balance. We've done that, but right now we have 0, of course. And then you are able to send it. So we could send it back to the testnet, or we could send it back to another canister address. And essentially, if we take a look at Chunky Bitcoin, if we take a look at the Minter canister, we can see that it has a Bitcoin address. No, it's not the Bitcoin address of the canister. Yeah, so this is the interface of the Minter canister, the Chunky Bitcoin Minter canister. So if we go back to the presentation in the beginning, I wanted to show you. This canister, it's the interface of this canister. And actually, it's really well explained. So you have all the methods on the interface that are described and explain exactly what they are doing. Convert Bitcoin to Chunky Bitcoin. So this returns an estimation of the fee that the user would pay based on the current status of the Bitcoin network. The minter is also going to charge. This one is for converting on the other side Chunky Bitcoin to Bitcoin. So retrieve Bitcoin. So yeah, that's about the minter, and then the ledger, which is accessible from here, is following the ICRC1 standard, and so we can check the total supply, for example, and we can of course specify transfers. So this is standardized way to do transfers, and we could also do approve and transfer from. So this would enable any application to transfer chunky Bitcoin on your behalf. If you approve and then do a transfer from, you would enable applications to transfer for you. Yeah, so sorry guys, I feel very sorry that we are not able to get our Bitcoin. I'll just check the balance one last time, maybe in the background it was settled, but otherwise I need to take a look at this testnet. The problem is I'm not too familiar with the Bitcoin side of things. I'm only familiar with the ICP side of things. So is there any gas fee when sending Bitcoin to ICP? Yeah, I've already answered that. P2P key hash is a public key hash. It's a simple way of creating an address. P2P SH is script hash. Think of it less. Okay, yeah. Bitcoin testnet addresses start with M or N. Testnet wallet can send to addresses with the prefix M2 or TB1. Okay, my address starts with a M. So I'm not sure why it's not working. Or at least why and also the first website didn't work, but the second one told me, give me like a transaction. I don't know. All right, guys. So let's close it here. Well, I hope you learn, at least if you want to really dive more into this Bitcoin integration, I'll give the link to the repository. So the repository I used, can take a look. And I'll wait for you in 10 minutes. We'll start the next session on HTTP outcalls. So this time we will attempt to connect our canister with a Web2 server, and we'll try to query the price of ICP from Coinbase. See you in 10 minutes, around 10 minutes. I need a little bit of preparation.